and welcome to today's lesson looking at the forces and elasticity required practical, which is part of the AQA GCSE Separate Science Physics course. So in today's lesson we're going to look and find the relationship between force applied and the extension of a spring experimentally. So we're going to try and describe what Hooke's law is, look at what the experiment is to prove Hooke's law, identifying a force extension graph where the inelastic and elastic regions occur, and then look at how you can calculate the spring constant for the force extension from the force extension graph. So it links into the following part of the AQA Separate Science Physics GCSE specification. So the forces and elasticity part of the forces module, which then links into required practical 6, investigating the relationship between force and extension for a spring. Now in previous lessons we've looked at the effect of a resultant force in the universe. So a resultant force causes an acceleration for an object. A resultant force can cause energy to change between stores. Now, a change in energy stores due to resultant force is called work done or mechanical work. Now, work can also be done when a charge flows in an electrical circuit. Now, there's also a third effect that a resultant force can have on an object. It can change the shape of an object, which we call the material deformation. Now, the first type of deformation is extension, which is when the resultant force, so therefore it is the combination of all the forces, will increase the size of the object. Now, a resultant force that causes this is called tension. Now, the second type of deformation you can get is called compression. That's when the overall resultant force will cause an object to decrease in size. Now, an object might not change in overall size due to resultant force, but it could be distorted, so it stays the same size but changes shape, and we call that idea bending. Now, there are two ways an object can behave if resultant force is applied to it. It can behave either elastically or inelastically. Now, an elastic object is when an object regains its original shape after the forces deforming it are removed. But an object is inelastic if the object doesn't return to its original shape after the forces deforming it are removed. It stays deformed. Now, it can sometimes be called plastic. However, we don't like to use the term plastic in physics because if people can get confused the chemistry definition of a plastic, which is a polymer. So in theory, there are objects which are not polymers can act plastically or inelastically in physics. Now, many objects will have an elastic and inelastic region depending on the deforming forces placed upon it and its size. So at lower forces, the object will act elastically, but at higher forces, the object acts inelastically. So an object is elastic if the object regains its original shape after the deforming force acting and are removed. An object is inelastic if an object doesn't return to its original shape if the deforming forces acting and are removed. Now, many objects are elastic at certain deforming forces, but then inelastic at larger deforming forces. Now, in all materials, the atoms of the material are bonded together. Now, in an elastic material, when the material is stretched, the bonds get stretched but don't break. That means that when the deforming force is removed, the atoms go back to their original shape. But if there's a large enough deforming force acting on it, the bonds between the atoms start to fracture, so the molecules lose their original shape and pattern. Now, this means the material becomes inelastic. Now, if there's a large enough deforming force placed on the object, the bonds between the atoms will eventually break. That causes the material to snap. So therefore the molecules are no longer in contact with each other. The material loses rigidity and then it breaks into two. Now, deforming force can cause an extension. Now, we can also consider this in terms of compression, which is possible for your examination, but in today's lesson, we'll only consider an extension. But please be mindful that it's exactly the same physics, except extension is getting larger and compression is getting smaller. Now, an extension is a difference in the length between when the deforming force is on it and the length when there's no deforming force placed on the material. So extension is the change in length of material, or delta L. So it's the length with the deforming force minus the length with no deforming force. Now, the greater the deforming force, the greater the extension of the object, but it's also true for compression as well. Now, In fact, it was found that extension and deformant force increase at the same rate for many materials, so they were in fact in direct proportion, which we call Hooke's law, because Robert Hooke was the first scientist who worked this out. So he realized that when you put force on the y-axis and extension on the x-axis, the line of best fit will be a straight line through the origin, which indicates that the two factors, force and extension, are directly proportional. However, it was only elastic objects that obeyed this particular relationship. So if the force extension graph of a material is a straight line, it obeys Hooke's law, it is elastic, force and extension are directly proportional. Now the graph has to go through the origin, as when the force is 0, the extension is 0. However, if a student has measured the length and not the extension, it wouldn't go through the origin, which is a common mistake which examination questions test upon. Now, Hooke realised that if a large enough deformant force was placed on the material, force and extension were no longer directly proportional, the material acted inelastically, so the line would start to curve. Now, the point in which this occurs is called the limit of proportionality. So after the limit of proportionality, the material acts as an inelastic. Now, eventually, like we mentioned before, if the material has enough deformant force placed upon it, the object will snap, which we call the breaking point. So, we know that if we plotted force against extension, you have an elastic phase for the material, where the line of best fit is a straight line, so the material obeys Hooke's law. Force and extension are directly proportional, but once you get to the limit of proportionality, the line starts to curve and the material behaves inelastically. Now, the gradient of the force extension graph is called the spring constant. Now, what we can do is, if we put the force on the y-axis and the extension on the x-axis, as we mentioned before, if it's an elastic object, we should have a line that goes through the origin, and also that's because, remember, force will cause extension, not length. So if it doesn't go through the origin, the experimenters measure the length, not the extension. So you can then have your straight line through the origin, and therefore you can work out its gradient, and that's the spring constant. Now, by definition, the spring constant is the amount of force needed to extend the object by 1 meter. It's how stiff an object is. So the stiffer the object, the larger the spring constant, the more difficult it is to extend, the more force you would need to extend it by 1 meter. Now, the spring constant can only be taken in the straight line section of the graph because it needs the gradient to be constant, so its spring constant can be constant, as the name suggests. Now, remember, how to work out a gradient? Well, you've got to draw a right-angled triangle on the graph where the line of best fit is the hypotenuse. Now, you try and make your gradient triangle as large as possible because this increases the validity of results because you're considering more values. Now, the gradient is the change in y over the change in x. So in this example, it's the change in force over the change in extension, so it's F over E. So because we know the gradient is the spring constant, we know its units are going to be the units of the y-axis, which is newtons, divided by the unit of the x-axis, which is meters. So the unit of the spring constant is newtons per meter, which makes sense based on our definition. Now, the spring constant is basically a proportionality constant between the deformant force and the extension it causes. So for a material that obeys Hooke's law, the deformant force is equal to the spring constant times by the extension. But that's only true for elastic objects, not inelastic objects. Now remember, a deformant force can also cause work to be done, so it allows energy to be stored as elastic potential energy in the object. Now you've learned that equation in paper 1 in the energy module, which we know is elastic potential energy stored is a half times by spring constant times by extension squared. Now the deformant force equation needs to be memorized for the examination. Now here's an example of the equation. So a spring has a spring constant 25 newtons per meter. How much force need to make the spring extend by 0.10 meters? Well, force equals spring constant times by extension, so it's 25 times by 0.1, 2.5 newtons. Now, as we mentioned before, if it's obeying Hooke's law, it should be a straight line through the origin. However, if it starts to curve, it no longer obeys Hooke's law. So it's elastic when it obeys Hooke's law, it's inelastic when it doesn't obey Hooke's law, and it's directly proportional when it obeys Hooke's law because it's a straight line through the origin. Now, the point in which it is no longer directly proportional is when the line starts to curve. It's when it turns from elastic to inelastic. That is the limit of proportionality. And finally, the graph finishes at the breaking point when the bonds between the atoms of the material sever and break. So, your required practical is trying to prove the relationship between the deforming force and the extension for an elastic spring. Now, what do you need to have for this particular practical? You need a clamp stand, a clamp, ruler, a boss, spring, a G-clamp, a pointer, and a 10 1 Newton weights. So you'll set up the apparatus as follows. So you'll get a clamp stand as such. You will then attach a boss to the clamp stand and you'll attach a clamp. You'll then put a counterweight on the clamp stand to stop it from toppling over, which is an important idea in your safety procedures. You'll place the clamp so it hangs over the table edge, so it allows the spring to fully extend without hitting the table. Okay, as such, you'll then place a meter ruler vertically in the clamp. Now, it's very, very, very important the ruler is in parallel because it reduces what we call parallax error when reading the length of the spring. Now, to help you set this up, you would use a set square to ensure that your meter ruler is vertical. Now, you place the top of the ruler in the clamp, which gives you most of the ruler to take measurements with. You'll then get a spring. Now, you need to ensure the spring is elastic, so don't deform it with your hands before you use it. You just put it on the clamp and get ready to go. So you set it up as follows. What you then do is you measure the original length of the spring. Now, I would measure from the top coil of the spring to the bottom coil of the spring. So it's a bit like this. Now, technically, as long as you measure between the same 2 points in the investigation, it doesn't matter which points you pick, but these are the most distinguishable parts of the spring. Now, to help you measure the particular parts of the top and bottom coil, you should use something called a fiducial marker. Now, a fiducial marker is basically a pointer that allows you to identify the length of a material very easily. Now, the most obvious example of a fiducial marker we can use is another ruler. Once you've done this, you'll retrieve 10 1 Newton weights. Now, these will be used to apply a force on the spring. Now, remember, the holder itself has a weight of 1 Newton. It's such like that. So you get a weight of 1 Newton, you'll place the weight on the spring, and then you'll measure this new extended length. And then from that, you can work out the extension, because the extension is the extended length minus the original length. Now, again, using a fiducial marker to do this reduces the error in the investigation and makes the result more accurate. It's such like that. Now, it reduces this parallax error, which you could possibly have if you don't set up your equipment correctly and you don't stand exactly parallel. Now, you've always got to check before you move on to your next result that the spring is still elastic. So to check it's elastic, it's got to have the same length as it after the deforming force is removed as it did before. So you remove the 1 Newton force from the spring and you measure the original length. Now, it should be the same, but you should always check that. Now, again, to measure the original length, you use the fiducial marker to make it more accurate by measuring the top and the bottom coils. And you'll do the same now for a 2 Newton weight and follow the same procedure. You'll do 2 Newtons, 3 Newtons, 4 Newtons, 5 Newtons, 6 Newtons, 7, 8, 9, and 10. Now, just remember again, extension, which is what you should be recording, is the extended length minus the original length. And always use your fiducial marker to reduce the error involved. Now, you should record your results in the following results table. So you'll have your original length, your stretch length, and your extension, where extension is the stretch length minus the original length. Then what you would do is you draw a graph with the force on the y-axis and the extension on the x-axis, and you should draw a line of best fit in, which should be a straight line of best fit through the origin, and then the limit of proportionality will be when that line of best fit starts to curve, and the gradient of the straight line section of the graph is the spring constant, because that's when it's acting elastically. So it's when it's acting as an elastic potential energy store. Now again, when you work this out, draw your gradient triangle as large as possible because it increases the validity of your results. So here are an example of some results you can gain in this particular practical. Now note a few things here. That all values in each column should be given to the same number of decimal places, and you should give all headings with a unit. Now, the number of decimal places is decided by the number of decimal places the measuring device can record to. So if your ruler can record to 3 decimal places, you write your result to 3 decimal places. So that's a very, very important concept. Now, in your graph, okay, you should draw your line of best fit in when you've got your force on the y-axis and your extension on the x-axis. Now, make sure all your axes are labelled with headings in units, your plots are plotted correctly, you've got an appropriate scale, and you've drawn a line of best fit. Now, you can see from my data that I didn't actually reach a limit of proportionality. The spring stayed completely elastic because the line has not yet started to curve. Now, you can then use your graph to determine the spring constant of your spring. Now again, you should draw your gradient triangle on there as large as possible to get the most valid results, and then you do your gradient is the change in y divided by the change in x. So in my particular investigation, it was 27 newtons per meter. So the spring constant meant I would need 27 newtons to extend my spring by 1 meter. Now you should always give your gradient values to the correct number of significant figures with the correct units. So here, 2 significant figures and the units of newtons per meter. So just to clarify, the extension of an elastic object is directly proportional to the force applied, providing that the limit of proportionality is not exceeded. So force equals spring constant times by extension, and that a force that stretches or compresses a spring does work and makes the spring an elastic potential energy store, and provided it's not inelastically deformed, the work done on the spring and the elastic potential energy stored are equal, which is equal to a half times by spring constant times by extension squared. So if you've learnt in today's lesson, you can describe what Hooke's law is, carry out an experiment to prove Hooke's law, identify a force extension graph where inelastic and elastic regions occur, then calculate your spring constant from that force extension graph. Hope you've enjoyed today's lesson and I hope you have a lovely day.